Hello everyone, and welcome to this week's Diffusion Seminar. My name is Woojin Kim from Dyson Lab at Seoul National University. So far in the seminar series, we've looked at the fundamentals of diffusion models, especially in the vision domain. We have discussed how these models work at the technical level, from the forward noising process to the reverse denoising process, as well as the underlying architectures and training objectives. Beginning today, we'll shift our focus from images to text. Specifically, we'll be talking about diffusion language models, or DLMs. These models adapt the diffusion framework to natural language generation, which brings unique challenges compared to vision, but also exciting opportunities. This first part of the lecture will introduce the motivation, key differences from auto-rigorous models, and the technical adaptations required to make diffusion work in language. In later sessions, we'll dive deeper into training objectives, sampling strategies, and recent advances. So, let's begin with the basics of what makes diffusion models for text both challenging and promising. Today's talk will follow a simple flow. We'll start by moving from the vision domain to the language domain. Then, I'll highlight the main challenge we face, the discreteness of text. Next, we'll see how diffusion language models can be categorized into two families, the continuous and the discrete. In this session, we'll focus on continuous DLMs, and in the next session, we'll dive deeper into the discrete ones. Until now, we have mostly lived in the vision world, adding noise to images and learning to denoise them back. From here on, we'll shift to language and focus on what carries over and what breaks. Some kind of ideas transfer nicely, like noise schedules, score matching, and iterative refinement. However, text brings new issues. It's discrete. It has order and variable lengths, and semantics can flip with a single token. In the next few slides, I'll map the vision intuition to language, highlight the gaps, and lay out a simple framework for handling them. Let's start with what makes text fundamentally different. First, the quick recap before we jump to language. We have covered the core diffusion algorithms, the DPM, the stochastic Markovian denoising step by step, and the DDIM is the deterministic non-Markovian sampling that trades a bit of stochasticity for speed and quality control with fewer steps. We also looked at continuous time variance as SDE and ODE formulations. Then, on the modeling side, we studied architectures and working spaces. Pixel space units evolved into DIT, the transform backbones, and latent diffusion moved generation to a compressed latent space for efficiency. Then, for the guidance, we have seen classifier guidance, classifier-free guidance, and related conditioning tricks that steer samples toward prompts or attributes. The key pattern across all of this is that images live in a fixed dimensional, continuous space, and we apply continuous corruption, such as Gaussian noise with smooth denoising dynamics. This assumption will be exactly what breaks when we move to the text domain. Diffusion models clearly work well in the vision domain. However, when we turn to language generation, things look a bit different. Language is inherently sequential. Humans naturally speak word by word, and most of our models so far, like auto-rigorous transformers, follow this left-to-right process. So, the central question is, if diffusion is iterative and parallel by nature, can it really be applied to a task, something like text generation, that seems so sequential? Even though language is sequential, humans doesn't always generate sentences strictly from left to right. Sometimes we sketch out the core ideas first. For example, words like cat, chase, and garden like nouns, and only later fill in the smaller connecting words. This gives us a simple rationale. Language generation can also be viewed as an iterative refinement process. Instead of committing to a rigid sequence from the start, we can start with rough content and progressively refine it into a complete sentence. Recent work points out that auto-rigorous decoding can actually be seen as a special case of diffusion. Here's the idea. In diffusion, we normally generate by repeatedly updating tokens, possibly in any order. If we fix the update order to always be left to right, then that process reduces to standard auto-generation. For example, suppose we want to generate the sequence the cat runs. In a diffusion framework, we could start with all positions masked and then gradually fill them in, sometimes starting from the middle, sometimes the end. However, if we restrict the diffusion process so that at step 1 we always feed position 1, and step 2 we always feed position 2, and so on, then the model's behavior is exactly that of a left-to-right AR decoder. So AR is just diffusion with a rigid ordering rule. This perspective is powerful because once we relax this restriction, we can explore much richer generation strategies. Currently, autoregressive models already work very well. Then, so why should we even consider diffusion for the text? Here are 4 key benefits. First, the parallel decoding. In AR models, tokens are generated one by one, which limits the speed. However, with diffusion, all tokens can be updated in parallel. So, instead of waiting for a sentence like "the cat chased the mouse" to be written word by word, the model refines the entire sentence together, making better use of hardware and speeding things up. Second is the controllability. Diffusion integrates naturally with guidance techniques. For example, if we want the same sentence but with a positive sentiment, we can steer generation with a sentiment classifier, or classifier-free guidance. These techniques make targeted control, something like style, tone, or topic control, much easier. Then the third is iterative refinement. AR models lock in early mistakes. If the second word is wrong, the rest often fails apart. Diffusion instead allows repeated updates. So if the model first outputs "the dog chased the mouse," but later it realizes should be cat, it can correct itself during the refinement process. Finally, the bidirectional context. AR generation only sees the past. Diffusion, on the other hand, conditions on the full sequence. This is especially useful for tasks like infilling. If we have "the something chase the mouse," diffusion can consider both sides and generate the missing word coherently. So, these properties, the parallelism, controllability, refinement, and the bidirectional context, are what makes diffusion a promising direction for language modeling. Then, let's move on to the main challenge, the discreteness of the text. This is the key issue that prevents us from directly applying diffusion models from vision to language. In vision, diffusion is very natural. We start with a clean image, gradually add Gaussian noise, and train the model to denoise step by step. The key point is, even when noise is added, the intermediate samples are still valid images. Consider this cat photo. With some noise, it still looks like a cat. With more noise, it's fuzzier but still recognizable. It's only when we push noise to the extreme that it becomes pure static. This smooth degradation is what makes diffusion work so well in the image domain. However, the language does not behave this way. Text is made up of discrete tokens that contain pixels. For example, the sentence "the cat sits on the mat" is mapped to integer tokens like 0, 40, 43, or something. Then, imagine we add random noise to these integers. We'll get values like 0.5, 40.7, and things like that. Then, what does this mean? It's not a valid text anymore. It's just a set of uninterpretable numbers. We can think of, okay, just round them back to integers, but this doesn't solve the problem. A tiny numerical change can map to a completely different token. So instead of "the cat sits on the mat," rounding might give something nonsensical like "no image y on the love." This is the core issue. Text discreteness breaks the smooth noise and denoise process that works so well in images. In images, small perturbations are usually harmless. If a single pixel changes from brown to red, the picture is still recognizable as the same object. The internal meaning does not change. However, in text, things are very different. Even a single token change can completely alter the meaning or make the sentence ungrammatical. For example, "my cat ate a fish." If we change just one token, cat becomes car or A becomes B. Now, the sentence becomes "My car ate big fish," which is entirely nonsensical. This kind of fragility makes it much harder for diffusion in text. Noisy intermediate states don't necessarily respond to valid or fluent sentences, unlike in images. In standard diffusion for text, we usually add and remove noise at the token level, treating each position as if it were independent from the others at every step. However, language isn't like that. Words are connected by strong sequential dependencies: the syntax, semantics, and the ordering. If this kind of links are broken, the sentence quickly loses coherence, especially in long-form text or structured outputs. Therefore, several approaches have been proposed to adapt diffusion to the text domain, and broadly, this can be categorized into two big families of diffusion language models. In the next section, we'll go through these two directions one by one. To apply diffusion to language, we need to overcome the discreteness problem we just saw. And broadly, researchers have taken two directions. The first is continuous diffusion. Here, we map text into a continuous space, like embeddings, and apply diffusion there, just as we do with images. Then, the second is discrete diffusion. Instead of going continuous, we kept the process directly in token space, and define corruption and denoising in a discrete way. These are the two big paradigms for diffusion language models, and in the next class, we'll look at each in more detail. To apply diffusion in a continuous way, we first need to make text continuous. That means embedding tokens into a continuous space, either the embedding space of tokens or a compressed latent space. Once the text is mapped into this space, we can add Gaussian noise and denoise iteratively, just as we do in images. At the end, we map the result back into valid tokens, either by rounding to the nearest vocabulary entry or by using a decoder. Most of the earlier diffusion language models follow this approach. For example, diffusion LM applies noise directly in the embedding space, while LD4 and Agile uses a latent compression network before applying diffusion, making the process more efficient. So, in short, continuous DLMs borrow heavily from image diffusion, but they require this extra embedding and decoding step to bridge back to the discrete text. The other family is discrete diffusion language models. Instead of embedding tokens into a continuous space, these models operate directly in token space. The idea is quite simple. Progressively corrupt the sequence with symbolic operations like random replacement, masking, or shuffling, and then train the model to denoise this. Earlier works like Diffusion BERT started with masking-based corruption, and later models such as SAD or LADA refined this approach for longer and more structured text. So, unlike continuous diffusion, where we rely on embeddings in Gaussian noise, discrete diffusion stays true to the symbolic nature of the text. Then, let's make a simple comparison between the two families. First, the continuous diffusion works in embedding or latent space. Here, noise is added in a continuous way, just like in images. The main pros for that is support classifier guidance. Also, it can leverage existing image-based techniques. And finally, single-step operations can be more efficient. But the cons are first training instability, then scaling to a very large corpora is still unproven, and finally it always requires encoder and decoder modules to bridge text in continuous space. Discrete diffusion, on the other hand, operates directly on token space. Its noising process is symbolic, and the pros are that it works directly with tokens. It aligns more naturally with existing NLP models, and the training objective is much simpler. The cons, however, are that classifier guidance is more limited, and also the corruption recovery transition is not differentiable, which makes optimization trickier. Thus, each paradigm comes with strengths and trade-offs, and different works explore them depending on the task. Now that we've seen the two big families, for the rest of today we'll focus on the continuous formulation of diffusion language models. We'll go through how they actually work, how text is mapped into a continuous space for diffusion, and what kinds of methods have been proposed in this line of research. So let's start by unpacking the basic workflow of continuous DLMs. One of the first works in this area is Diffusion LM. The idea is quite simple. Since text is discrete, they first embed tokens into a continuous space. This allows to apply the same Gaussian noising and denoising process that's used in vision diffusion models. Looking at the figure, on the left, we start with Gaussian noise and gradually denoise step by step, exactly like in the DPM. Once we recover the clean continuous representation x0, we then round it back to the nearest token embedding, giving us actual words again. So, first embedding, then to diffusion in continuous space, then finally rounding back to the tokens. This design was one of the earliest attempts to make diffusion work for the language. Because diffusion LM inserts embedding and rounding between the text and the diffusion core, the loss cannot be just the vanilla DPM term. We start with the standard DPM objective over the denoising steps. Then, we add terms that account for the bridge to text, the embedding consistency term, and the likelihood of rounding back to tokens. This gives the end loss you see in the middle box. However, they observed that predicting noise and embedding space is unstable and doesn't couple well with the rounding step. So they switched targeting to predicting x0 directly, the clean embedding before the noising process. The final objective is simple L2 reconstruction on x0, which empirically trains more stably and aligns better with the discrete decoding at the end. Diffusion LM also mainly emphasized the controllability aspect of diffusion for text. As we have discussed earlier, one powerful feature of diffusion is the ability to plug in classifier guidance during sampling. The mess here is essentially the same as in image diffusion. Start with the conditional probability of the whole denoising chain given a class, apply bias rule, and under a conditional independence assumption, we separate the model likelihood and the classifier likelihood. This gives us the final form. The gradient update has two terms, one from the denoising model itself and one from the classifier. In practice, this means we can steer the generation towards specific attributes, for example, syntax structures, sentiments, or topics, while still denoising the continuous space. One another technique that became quite common in the continuous formulation is MBR decoding, the minimum bias risk decoding. Because diffusion is inherently noisy and works in parallel over tokens, the generated outputs can sometimes be unstable or ungrammatical. To address this, instead of trusting a single sample, the model generates many candidate sentences. Then, using an external metric, for example, negative BLU score, it selects the candidate that is most consistent or fluent. So, the pipeline looks like this. Generate multiple outputs, then compare them with the objective function, then finally pick the best one. This decoding trick has been widely used to compensate for the relatively lower quality of raw samples in continuous diffusion models. Then, the diffsec is an extension of diffusion LM that brings diffusion into sequence-to-sequence tests, such as translation, summarization, or dialogue generation. The key idea is that the input sequence doesn't need to be noise or denoise. Instead, only the target side is diffused. This is done with the partial noising. Gaussian noise added only to the target embeddings during the forward process. Then, during denoising, the model is conditioned on the input sequence at every step, so it can gradually refine the noise target into a fluent output. This makes diffusion unusable for conditional text, while keeping the input side intact. Also, one of the main issues in continuous diffusion LMs is embedding collapse. Because noise is added in the embedding space, the embeddings can drift and collapse into indistinguishable points. This often leads to degeneration, where outputs lose diversity and collapse into repetitive or nonsensical patterns. The former tackles this by introducing anchor embeddings that act as reference points, helping stabilize the denoising process and maintain diversity. However, it's important to note that the embedding collapse remains a persistent challenge in the continuous framework. Even with these fixes, it is one of the major obstacles for scaling continuous diffusion language models effectively. Next, Let's look at two other important continuous diffusion approaches. First, LD4LG. This method is inspired by latent diffusion in vision. Instead of directly diffusing embeddings, it uses a pre-trained encoder and decoder, like BART or TIFF5, to compress the input text into a fixed-length continuous latent space. Diffusion then operates in the compressed space, and finally, the decoder reconstructs the text. The main benefit here is efficiency. Operating in a lower dimensional latent space saves time and makes diffusion more practical. Then, SSD-LM tackles two limitations of continuous frameworks. First, the fixed-length generation, which restricts flexibility, and instability from embedding collapse and classifier incompatibility. Their solution is twofold. First, they adopt a semi-autoregressive decoding generation process in blocks, allowing partial parallelism while still keeping some order. Second, they introduce a simplex space formulation, which maps logits into the probability simplex. This lets the model operate directly in vocabulary space, effectively bridging the gap between continuous and discrete formulations. So far, we've looked at how continuous diffusion LMs are built. Now, let's see how they are actually used. A big advantage here is controllability. It's easy to plug in external classifiers for sentiment, style, or topic control. Also, because diffusion involves stochastic multi-step sampling, it naturally generates diverse outputs. This makes it well suited for applications like controllable text generation, style transfer, and even artistic or creative writing. One of the most common downstream uses is controllable text generation. Here, diffusion alone can generate text under constraints like syntax, length, or semantics. For example, producing sentences that match a given parse tree. SSD-LN also supports this, adding fine-grained sentiment control. The key takeaway is that diffusion makes control easier and more systematic compared to standard autoregressive decoding. Diffusion has also been applied to text style transfer. For example, DeepSec style PTB can convert sentences across tenses or syntactic forms. Another model, ParaGuide, adds style or formality control by conditioning the diffusion process on paraphrasing signals. This kind of applications highlight how diffusion models can reshape text structure while preserving meaning, a very challenging task for autoregressive models. Diffusion is also finding creative applications. For example, poetry diffusion generates poems while jointly controlling for rhyme, tone, and metrical structure. On the right, you can see a generated sonnet where both semantic coherence and the AB rhyme pattern are also respected. This demonstrates how the controllability of diffusion models can extend into highly structured artistic domains. This wraps up our discussion of continuous diffusion language models. Next week, we'll move to the other side of the picture, the discrete diffusion LMs. We'll look at how masking and absorbing states are used to corrupt and recover token sequences, and why token ordering becomes such an important design choice. Then, we'll also compare autoregressive and non-autoregressive setups, see how AR-like formulations can be integrated into diffusion, and finally explore block-wide diffusion as a middle ground. So, in short, today we've seen how to make discrete text continuous for diffusion, and next week we'll flip it around and study how to stay fully discrete while still benefiting from the diffusion framework. Thanks for listening. If you have any questions, do not hesitate to email me at this address. Thank you.